Hi everybody. So we've been talking about thermodynamically or favorable or spontaneous processes and reactions. And we said that the two driving forces in nature that determine whether the reaction is going to be thermodynamically favorable or spontaneous are entropy and enthalpy. So nature prefers the spread of matter and the spread of energy. So in terms of the spread of matter, we talked about entropy, that we want the products to have more entropy than the reactants, more disorder. And so we want delta S of our system to be positive. That's favorable. In terms of energy, remember that the first law of thermodynamics says that the total energy in a closed system is constant, right? And so when we're studying enthalpy, we had talked about the system and the surroundings. And so here's your system, and then your surroundings. So we said when the system releases energy to the surroundings, that's an exothermic process, but when the surroundings give energy to the system or the system absorbs energy, that is an endothermic process. So which one would be favorable by nature? Well, let's think about, when delta H is positive. So that's endothermic, right? Well, if it's an endothermic process, that means the system is absorbing energy from the surroundings, right? So you're taking energy that is spread out all over the surroundings, and you're taking it and putting it into your system. You're concentrating it into your system. That's not good, because nature prefers the spread of energy. And so that would not be thermodynamically favorable. So this is not favored. If you have an exothermic process, that would be favored. And the reason for that is because you're taking energy from your system. So your small system, you're taking the energy from it and you're giving it to the surroundings. So you're spreading it all over the surroundings, and that is favorable. So exothermic processes are favored in terms of energy or in terms of enthalpy by nature. So let's look at these here. These are the same processes that we looked at in terms of entropy, whether they are entropy driven or not. Now we're going to look at whether they are enthalpy driven or not. So we want to indicate the positional energy, if it's greater for the reactants or the products. We want to indicate the sign of our enthalpy change, which is our delta H, and then whether the reactions are enthalpy driven or not, favored by enthalpy or not. So same exact processes and same exact questions, except we're talking about delta H here, enthalpy, instead of delta S, which is entropy in the first page. So CO2 gas going to CO2 solid. So which one has more potential energy? Well, gases have more potential energy, right? And so the reactants here have more potential energy. Let's look at the sign for delta H. So if you're going from gas to solid, the gas has to release some energy in order to become a solid, which is lower in potential energy. And so our delta H is negative. It's an exothermic process. And so is that favored? Yes, it is. It is enthalpy driven. Okay, let's look at B. KCl solid, and we're going to take that solid and we're going to dissolve it. So we're going to get the aqueous ions. Which one has more positional or potential energy? Well, let's think about this. In order to dissolve a solid, you got to break your crystal, right? And so if you're breaking the crystal, that means that you're putting in energy in order to break it, which means it's endothermic. Your products actually have more potential energy. Your delta H is positive. Again, because you know that because you need to break the crystal in order to get to the ions. And breaking a crystal would be endothermic. You got to put in energy in order to overcome the lattice energy, right? So that would be not enthalpy driven. Okay, let's look at the last one here. So MgCO3 plus heat yields MgO plus CO2. Well, we can see from this that the heat is on the reactant side, which means that the system is absorbing that heat, which means that it's an endothermic process. So my products have more potential energy here. Delta H is positive. It's an endothermic process, and so this is not enthalpy driven. Okay. So in each of these processes, you have to be careful. Are you asked about entropy? Or are you asked about enthalpy? Or are you asked about both? Because they won't always agree. Sometimes, you know, they're favored both by entropy and enthalpy. Sometimes they're neither. And sometimes it's favored by one and not the other. So I'm going to be careful what you're asked about. In terms of calculating enthalpy, delta H of our system, there's many ways that we've learned how to calculate that. The most common for this chapter is going to be heats of formation, products minus reactants. And again, you're going to use your table of thermodynamic values here. And on the test, you wouldn't be given the whole table, but you'd be given the ones that you need. Remember that heat of formation of an element in its natural state is equal to 0. But if you have something that's not in its natural state, or if you have a compound, then it's not going to be equal to 0. Versus the entropy is never going to be equal to 0. So watch out for that also. So to calculate delta H of the reaction, as we've always done before, you're going to take the heats of formation of the products minus the heats of formation of the reactants. And the next time, we're going to learn about how you can put entropy and enthalpy together. Have a great day.